Chemistry of life. This is going to be a quick review of some chemistry concepts so we can then get into some biological concepts. So first thing, start with the atom, atomic structure. Atoms are made up of protons, electrons, and neutrons. So these are the three subatomic particles that make up an atom. And the mass of an atom, how much it weighs here on Earth, or its mass, we'll use them synonymously, but essentially its weight comes from the protons and the neutrons, which are both found at the center of the atom. The electrons are there. They're not at the center of the atom, they're around the center of the atom, and they are much smaller. They have very little mass. So when we go to draw these atoms, we use, these are Bohr Rutherford diagrams here, but we will be showing the nucleus in the middle there. It has the protons, which have a positive charge, and the neutrons that have no charge, meaning that the nucleus will end up with a positive charge because the neutrons don't have any charge and the protons have positive, so it ends up being positively charged in the nucleus. And then the electrons, which are not in the nucleus, they are outside of the nucleus, we'll draw them as being around there. They have the negative charge. So we'll draw some Bohr Rutherford diagrams with these ones. Depending on what atom you're dealing with, there's different number of protons or neutrons in the nucleus itself. It is the number of protons that determine which element you're dealing with. So a carbon atom has a 6 protons in the middle there, and then it can have varying amounts of neutrons, but it tends to have one amount is going to be more common than the other. Oxygen is going to have a different number of protons, making it a different atom. So it's a number of protons in the nucleus that determines which element you're dealing with. If it's a neutral atom, the electrons on the outside, these negatively charged electrons on the outside, will be equal to the amount of protons on the inside. That means it's going to be a neutral atom. The positives and the negatives are the same, so they cancel out and it has no overall charge. It's a neutral atom. If they're not the same, and we'll get into ions in a minute, if they're not the same, then it is going to be an ion. So these Bohr Rutherford diagrams, quick way of depicting the atom. And so boron, if you look at boron on the periodic table, it is the 5th element in. So being element number 5, that means it has 5 protons. So we can draw the nucleus in the middle here with 5 protons. And different amounts of detail you might want to put into a Bohr Rutherford, but getting the number of 5 protons in the middle, that's sort of one of the basic things. Now the weight of boron, if you look on your periodic table, it says boron weighs about 11 as its atomic mass. And so if its weight's made up of the protons and the neutrons, and if the weight equals 11, and there's 5 protons, then the missing mass that is made up of the neutrons must be 6. So most borons tend to have 6 neutrons. Now remember, it's not the neutrons that determines which atom you're dealing with, it is the protons. The neutrons can vary, and it can still be the same element. So there might be some boron atoms that don't have 6 neutrons, but every single boron atom, the thing that makes it boron is the fact that it has 5 protons. If it is a neutral atom, it is not an ion, it does not have a charge, these 5 positively charged protons have to be balanced with 5 electrons. So how we draw them is we have a shell, we'll call it. We just draw a circle. And so this shell here, there's going to be a number of different ones. Let's draw a slightly better one there. So this first shell can only hold 2 electrons. So we can draw one there, and we have one drawn there. Now that fills up that first shell. So the rule is that the nature of the universe is that that first shell can only hold 2 electrons. But you see that boron has 5 electrons, right? Because if it has 5 of these positively charged protons, then it also has to have 5 electrons in order to be neutral. So we need, if 2 can only fit in the middle there, we're going to, in the first shell, so we're going to need another shell to fit the other remaining 3. So we can draw another shell, and you can sort of play around with exactly where you want to draw these, but we tend to space them out the top, the sides, and the bottom, put one in each spot before we double them up. So this first shell can only hold 2 electrons. This second shell is only holding 3 for boron, but it could hold up to 8. So that would obviously give you room for 10 electrons. And then if we needed to, we don't for boron, but if we did need to, say for a large atom, we can draw another shell once we've filled in our 2 and our 8. And our third shell will also hold 8 electrons. Once you get past like 20 electrons, we don't really use Bohr Rutherford diagrams anymore. So really 2, 8, 8, and then feel free to put 2 in the last one. You'll get to calcium, that'll give you 20 spots for electrons. After that, we don't really use Bohr-Rutherford diagrams. All right, so this gives us a quick outline of what these atoms look like. And again, your periodic table is going to arrange them for you. Not only does it put them in order, but it also groups them based on their properties, which is really important to see. But for biology, a lot of the atoms that we're going to be using are outlined here in yellow. So we're going to be using hydrogen very, very often. We're going to go on and talk about carbon in detail. So carbon and hydrogen are going to make up a big component of biological molecules. Then we have these other ones here, nitrogen, oxygen, phosphorus, and sulfur, that are also a big part of biological compounds. It's not that the other atoms aren't found in biological molecules, it's just that they're not found in the same amount. And some of them you don't find at all. But these 6 that are depicted on the slide, these are the main ones that we're going to be using in biology. All right, quick definition on isotopes. Isotopes are, as we mentioned with, I think it was boron, you can have the same element but have a different number of neutrons. Remember, if you change the protons, you don't have the same element anymore, right? So if it is to be an isotope, it has to be the same element, which means the same protons, the same number of protons. So boron has to have 5 protons. That's it. If it has anything else, it's not boron. But what you could have is you could have boron with a different number of neutrons. So those neutrally charged particles that are in the nucleus, if you have a different amount of them, you have a different isotope of that particular element. So here's some examples of them. So for example, hydrogen, we often depict its mass up in the, as like sort of a leading superscript. So if you see a hydrogen with a 1 up top, what they're trying to tell you is which particular hydrogen is, and they're trying to say, okay, the mass of this hydrogen is 1. So essentially we put the atomic mass, when we're doing it short form, we put the atomic mass up in the top left-hand corner there. This would tell you that hydrogen's mass is 1. So it must only have 1 proton. And if its mass is 1, it has 1 proton, then the number of neutrons must be 0, right? It can't have any neutrons, otherwise its mass wouldn't be 1, because it has to have a proton in order, 1 proton in order to be hydrogen. But there's an isotope of hydrogen which has a mass of 2. So when we're doing atomic notation, we can put that little superscript of 2 in front of the hydrogen, and that would say, hey, this hydrogen's mass is 2. Now, it can't have 2 protons, because if it does, it wouldn't be hydrogen. It would be helium. So if it's hydrogen and it has a mass of 2, then it must have 1 proton, because it's hydrogen, it has to. And the rest of the mass would be that 1 neutron. Put the 2 together, you have an atomic mass of 2, and that's what's being depicted in the atomic notation. Then there's this other type, so you can imagine this is sort of your regular hydrogen with no neutrons. Here's this special deuterium hydrogen with 1 proton and 1 neutron. And then there is this other type, which appropriately is called tritium. It is hydrogen still, but it's an isotope of hydrogen. So these are different names of these particular isotopes of hydrogen. And of course, since it has 2 neutrons and 1 proton, its atomic mass is going to be 3. With carbon, so here's carbon, and so you can see the way it's written in atomic notation. It has a superscript of 12 written in front of it. Don't get that confused with a subscript or a superscript on the right-hand side. This is a left-hand side superscript, so this is what we use when we're doing atomic notation, and it says that this mass of carbon is 12. But if you look at your periodic table, carbon's the 6th element in, so it must only have 6 protons, because if it had any more protons, it wouldn't be carbon. So carbon has 6 protons. So if it weighs 12, then 6 of that weight must be the protons. The remaining 12 minus 6, the remaining 6 must be neutrons. So that would be carbon 12 is how we call it. It's a carbon atom and it weighs 12. Then there is an isotope of carbon 12 that actually has 2 extra neutrons in it. So because it weighs 2 more, its mass is 14, and we can depict that with a leading superscript. So carbon 14 would have, again, it has to have 6 protons. If it doesn't have 6 protons, it's not carbon. But if it weighs 14, then the remainder of that weight is made up of neutrons. And you can see 8 neutrons for carbon 14, 6 neutrons for carbon 12. Carbon 14 and carbon 12 are isotopes of each other. All right, ions. These are when you are not looking at the nucleus of the atom, so you've got your protons and neutrons in the nucleus, they're doing whatever they're doing. But if you're instead, you're looking at a difference in the electrons around the outside of them. If you change that number of electrons from what it would be normally for a neutral atom, then you have what's an ion, what is called an ion. So atoms which have either gained or lost electrons. So that number of electrons can be changed by, some atoms like to lose their electrons, some atoms like to gain their electrons, and if they do that, that will create an ion. Now remember, electrons themselves have a negative charge. So if you subtract a negative charge, you end up with a positive charge. You're starting at 0, and if you lose negatives, you become more positive. If you gain negatives, you become more negative. So these ions will have charges accordingly. The ones that have lost electrons, therefore they get this positive charge, we call them cations. And there's a nice positive looking T in there to help you remember that. So cations have lost electrons and become positively charged. Anions have gained electrons and become negatively charged. So those are the two names of the types of ions. Now, depending on which atom you have, it's going to be more prone to do one or the other. For example, sodium, and here's a nice Bohr-Rutherford diagram for sodium. It is number 11 on your periodic table, so it's got 11 protons, and normally it would have 11 electrons around the outside. So you can see again, the first shell, we're trying to get to 11, so the first shell has 2, the second shell has 8, and the third shell has 1 in order to get us to 11 electrons. So that's where all those 11 electrons are for your neutral sodium atom. But it could form an ion. So what sodium likes to do, as with all metals, it likes to lose its electrons, because by doing so it ends up with an outer shell that is completely full, and that's something atoms love. And so it will lose 1 electron, and in doing so, it's gone from having 11 electrons down to having 10 electrons, but the nucleus remains the same, because if it changed, you'd have, if protons change, it wouldn't be sodium. If the neutrons were different, it would be different isotope. So we're not talking about that. We're talking about the electrons. We're talking about ions. So we have changed the number of electrons from 11 down to 10. So you can see there's a surplus of positive charge. There's still 11 positives in the middle, but there's only 10 negatives on the outside. Therefore, sodium as an ion has a positive 1 as its charge. Same work for chlorine, but in a slightly different way. So again, chlorine wants to have a full outer shell. So what it's going to do is, if you look at it, its number, so chlorine is number 17. So we have 2 electrons on the first shell, total of 17 that we're trying to get here, 8 on the second shell, and then if you look at the third shell, we can fit 7. Remember, it can hold up to 8 on that third shell. So that's the arrangement of the electrons around chlorine. It would be more stable, it'd be happier if it could have a full outer shell. So what it does is it will gain electrons, and it will become, again, an ion. In this case, it becomes a negatively charged ion by gaining 1 extra electron in the outer shell. So now it is going to have 18 electrons in the outer shell, 17 protons still in the nucleus. The nucleus has not changed. And so we have an extra negative. So it ends up with a -1 as its charge. Bohr-Rutherfords are great, but obviously they take a bunch of time. When we get into showing how atoms interact with each other, we probably don't want to do all that drawing. So what we have available to us as a model is a Lewis dot diagram. And anytime atoms get together and interact to become stable in the chemical sense of the way, not physics or anything like that, but when chemistry happens, it's going to be involving the electrons in the outer shell. So if you look at your Bohr-Rutherford diagram, you've got all these inner shells and you've got that one outer shell. The bonding and the transfer of electrons is always happening with the outer shells. So what a Lewis dot diagram says is, okay, well, let's just ignore all that inner shell stuff. Let's just focus on the outer shells. So if you look at something like a Bohr-Rutherford diagram for oxygen, this is just a slice of one, but you'd have the nucleus, and then you'd have your inner shell with 2 electrons, and you have your outer shell with 6 electrons to show all 8 electrons around oxygen. So that's great if you want to show all that. But what a Lewis dot diagram would say is, okay, if we're just going to be looking at the chemistry, the bonding, maybe the transfer of electrons, the sharing of electrons, we really just need to focus on the outer shell. So what a Lewis dot diagram says is, okay, let's just put the symbol for oxygen so we know which atom we're talking about, and then we're just going to draw the outer electrons as dots around them. And generally we start, so let's say, I don't know, we had neon. Generally we start by putting 1 electron at the top if it only had 1, and then if it has more, we put 1 to the right, 1 at the bottom, and 1 to the left here, and neon have has 8 in its outer shell, so we have to keep going. So we then start pairing them up until we have all of them drawn there. And we'd only ever be drawing 8 in the outer shell for our purposes anyways. Oxygen, having 6 in the outer shell, ends up with 6 little electron dots around it. So if we had fluorine, if you look at fluorine, it's number 9. So you can think, okay, there's going to be 9 electrons around a neutral fluorine. 2 go in the 2 go in the inner shell. But a Lewis dot diagram doesn't draw the inner shell. It ignores that. It's just going to be drawing the 7 in the outer shell to get to our 9 electrons. So then we have fluorine there with our 7 outer electrons. It has 9. We just don't draw the inner ones when we're doing Lewis dot diagrams. Sodium, 1 valence electron in there, 1 outer electron. Valence is another way of saying outer electron. So its Lewis dot diagram would just show 1. It's not saying sodium has 1 electron. It's saying sodium has 1 valence, 1 outer electron. This gets us into ionic versus covalent bonding. So these are 2 ways in which different types of atoms are able to become stable by using and interacting with other atoms. So they can form these bonds, they can form these different types of compounds by combining together, and by doing so they become more stable. One way they can do it, depending on who's coming together, it could form ionic bonding, or you could have covalent bonding. So ionic bonds, these are where you end up with the formation of ions, hence the name. Now, what's really important to understand about ionic compounds is that you don't have individual units of them. You have this entire giant crystal lattice structure. So this picture on the left is an ionic crystal. So you think of this as being like sodium chloride, table salt. It's going to have ions of sodium and it's going to have ions of chlorine around it. So if, let's say this is our sodium and that's our chlorine, but they would have transferred their electrons like we saw in order to be stable. Chlorine wants to gain an electron, sodium wants to lose an electron. So that can happen. So sodium ends up with a positive charge, chlorine ends up with a negative charge. But when this happens with ions, it doesn't just happen with a sodium and a chlorine. So we know that the formula for sodium chloride is NaCl, and it makes you think there's 1 sodium and there's 1 chlorine, but that's not the case. It's actually, there is 1 sodium for every chloride. So what you really should think about is ionic compounds, their formulas are not telling you really how many are there. They're actually telling you that there is a ratio of 1 sodium ion to 1 chloride ion. So when you see the formula of an ionic compound, think ratio, and they are ions. So they have a charge, and this is the ratio in which they are present. If you look at the structure, if you look at a piece of table salt, you don't have 1 sodium ion and 1 chloride ion. You have 1 gazillion sodium ions and 1 gazillion chloride ions. That's the thing you need to understand about ionic compounds. Molecules, a little bit easier to imagine what they're like in that they do form these distinct units. So when we write the formula H2O, there are 2 hydrogens and 1 oxygen, and they form a little group, and that's water. So molecules are a little bit easier to picture in terms of what their structures look like, because it's very definitive, right? There's just this distinct unit that is a molecule. That is not the case with ionic compounds. All right, what is going to determine how these atoms are going to interact with each other? Are they going to form ionic compounds, or are they going to form molecules? Is this property of the atoms called electronegativity. And essentially this is how much they want to gain or want to pull on electrons. They may actually gain the electron, or they may just hog it a little bit in the sharing of it. And so here's a periodic table, and you look at your periodic table, you can look up this particular property of the atom called electronegativity. Here it is here. And you'll notice that something like fluorine, and these can be rounded off slightly different. You might see slightly different values depending on which periodic table you're looking at. But fluorine ends up being pretty high. Oxygen's pretty high. Chlorine's fairly high. Nitrogen's quite high. And so what we see is that generally the trend is the further up to the right on the periodic table, the higher the electronegativity. So these ones over here, they really like to pull on electrons. Now, Ignore the noble gases because they don't really like to bond at all. Some of the bigger ones you can make do, but the other ones don't bond. So ignore the noble gases, and otherwise the trend is up and to the right, the electronegativity, how much those atoms want to hog electrons when they meet someone else. They might want to share them, or they might share them unequally, and this would be based on electronegativity. So if you put hydrogen and oxygen together, so if you take a hydrogen atom and an oxygen atom, they will share their electrons, but you'll notice hydrogen's electronegativity is 2.1. So hydrogen is 2.1, oxygen is 3.5. So what that means is oxygen has a greater pull on electrons. It's more attractive to those electrons. And so we know that we can make water out of hydrogen and oxygen, and actually, let's draw the bonds here. So we end up with hydrogen and oxygen actually bonded to each other. That bond shows that they're sharing those electrons, but oxygen has a greater electronegativity. So it sort of hogs the electrons, and that actually is going to lead to this property called polarity. So the nature of a bond, and I've drawn a molecular covalent bond in this water here. So the nature of the bond is based on the difference in electronegativity. We can calculate, just take the two numbers, find the difference between them, and you'll get some difference. And this is the bonding continuum. So these are labels that we put on the bonds formed between two different atoms. So that bond between oxygen and hydrogen, it has a difference between it, it would fall on this range here. And if it falls on the low end, we say, okay, that bond is a covalent bond. It's saying they're sharing them really nicely. They're pretty equal sharing between them. So for example, if you had like a nitrogen atom and another nitrogen atom, they can bond together, and they form a triple bond. We don't need to get in the details of it, but they can bond together is the point. And they are going to share those electrons between them. Now, obviously, I don't know what the electronegativity of nitrogen is, but whatever it is, it minus itself, the difference between the two is going to be 0. So 0 would fall right on the low end of this scale. So that means they are perfectly sharing their electrons between them. If you look at hydrogen and oxygen, I won't draw the other part of water, but just this one bond in water, there is another bond in water as well, but just this one bond in water is going to be an unequal sharing. So depending on where those differences fall on this line, we can label the bond a different type. As long as it's under 1.7, it is a covalent bond. There's like nice and equal sharing covalent bonds, and then there's not equal sharing covalent bonds. Still sharing, but not equal. Anything below 1.7 falls into that covalent bond, and these are molecules. If it's over 1.7 difference in electronegativity between the two atoms, like sodium and chlorine, then it is no longer a covalent bond, and therefore it is no longer a molecule. We want to think of it as an ionic crystal instead. So to look at this bonding, again, we can do this with the Bohr-Rutherford diagrams here, or you could do a little faster with a Lewis dot diagram. But remember, they're trying to gain or lose electrons to become stable. And having an outer shell is a great way to become stable. So if sodium takes its 11th electron and says, okay, if I get rid of that to somebody, my next shell is full and I'm happy. So that's what sodium does. Chlorine says, okay, I'm one electron away from having a full outer shell and being happy. So what it will try to do is it'll try to gain electrons. So sodium and chlorine, if you put them together, you got sodium that wants to lose one, you got chlorine that wants to gain one, good match. They will transfer their electrons, and you'll end up with a sodium ion produced for every chloride ion. Now remember, you're not going to get one sodium ion and one chloride ion. You're going to get 1 gazillion sodium ions and 1 gazillion chloride ions, and you'll end up with a crystal lattice structure, not a molecule. And what we can see is that if we look at the electronegativity of these two, there's going to be a larger than, so the electronegativity difference is larger than 1.7. Therefore, this is an ionic bond. Therefore, the stealing that I've drawn here, that's what we mean by ionic bond. An ionic bond. An ionic bond is formed when an electron is transferred from one to the other. And it is the larger electronegativity atom that is going to take the electron. Non-metal will take electrons from metals. Non-metals on the right-hand side. Remember, that's where the high electronegativity is. Metals on the left-hand side. That's tends to be low electronegativity, and that's why ionic compounds are made of metals and nonmetals. This, again, we end up with these ions here. There's this positive sodium and this negative chloride ion because they have gained or lost electrons. So we have a sodium cation and a chloride ion. Notice the name for the anion gets changed to ide at the end, so chlorine becomes chloride. All right, with covalent bonding, and this is going to make up a big part of biology. This is, we're looking at molecules and covalent bonding a lot more than we are looking at ionic compounds. Covalent bonding, we don't have the transfer of electrons. The electronegativity difference is going to be less than 1.7. So again, the difference in electronegativity is going to be less than 1.7. Remember, those are just labels, so it's not always perfectly less than 1.7, but it tends to be generally less than 1.7. Will give you covalent bonding, which means a molecule, which means a distinct unit, not an ion crystal. This is a sharing of electrons. And the closer it gets, the higher that electronegativity gets, the less equal the sharing is. We can also get multiple sharing between atoms. They can share one pair of electrons, and that makes a single bond. So one electron from one atom and one electron from the other atom, they get shared in the space between them. That's a single bond. If it happens twice, it's a double bond, and if it happens 3 times, it's a triple bond. We're going to be drawing these as lines when we go to draw actual molecules. You could think of this as overlapping areas where those electrons exist, and you can imagine if we're drawing the Bohr Rutherford, it gets really complicated really quickly. So we're going to get into drawing this shared area as lines instead of as these clouds. All right. Non-polar covalent. So polar is so important. We say when it's not polar, we can call it non-polar. And what this means is equal sharing, or pretty close to equal sharing. Polarity refers to differences, and so if the sharing is equal, there won't be any differences. So we say it's non-polar. It's like a double negative there. So electron sharing between atoms of equal electronegativity, or close to equal electronegativity. This means the electron is being shared equally between the two atoms. So you can think of it as, if we were looking at those sort of clouds of where the space where the electrons would be, think of it as sort of as likely to be near one atom as the other. And so oxygen, O2, obviously, since oxygen we're looking at 6 valence electrons. So let's quickly whip up a Lewis dot diagram. I'm going to put my electrons like, that's not 6. Where's the eraser there? All right, pretends that's 6. There we go. And I'm going to draw this atom with 6 electrons around it. Oh, did it again. And so to share these electrons, we can say, okay, each of these oxygens has 6 electrons around it. They want to have a full outer shell. Full outer shell is 8. So they're going to have 2 more electrons. But the electronegativity difference between 2 oxygen atoms has to be 0, right? Because they have the same electronegativity, so the difference has to be 0. So one oxygen can't take electrons from the other. So instead what they do is they share the electrons. So this oxygen has its own electron and this other oxygen has its own electron, but they could share that pair of electrons in a space between them. That's what a covalent bond is. We're going to not draw the dots and circle them. Instead what we're going to do is we're going to show a line. That line represents those 2 electrons, those 2 dots, being shared. And oxygen does it twice. So it takes its 6 electrons, and one oxygen shares 2 electrons with the other oxygen, and the other oxygen shares its 2 electrons with the first oxygen. So when you go to say, okay, are these oxygens stable? Are there 8 electrons around it? We've got 1, 2, 3, 4 as the original electrons on that first oxygen, plus this bond counts as 5, 6, and the other bond counts as 7, 8. So this oxygen has 8 electrons around it. So make sure when you look at those bonds, you see 2 electrons per bond, per line. And that is a shared pair of electrons. So both these oxygens are happy. That's a stable molecule. And because the electronegativity difference between these, so if we looked up the electronegativity for one oxygen and you subtract it from the other one, you would get 0. That is perfectly equal sharing. That is a pure covalent bond. A polar covalent bond is when you have unequal sharing, still sharing, but not equal sharing. So unequal sharing of electrons between two atoms. What this means is the one atom that has higher electronegativity hogs the electrons. And it's sort of like pulling on them. It's keeping them around it more often than it's around the other atom. So this leads to partial charges. The atom that has higher electronegativity is hogging the negative electrons, so it ends up with a slightly negative charge. Not an ionic charge, not that much, but it's just sort of hogging them, and so it ends up with a partially negative charge. The atom that's having them pulled away from it, not taken away, but sort of just pulled away, ends up with a partially positive charge. This is what we mean by dipoles. So a dipole is where you have, let's go back to our hydrogen and our oxygen. So we said that they'll form a bond, they'll share electrons, but since oxygen's electronegativity is higher than hydrogen's, we end up with a polar covalent bond. Oxygen is sharing these two electrons, but it pulls the electrons towards the oxygen, so it ends up with a negative charge. It's not a full negative charge, so what we do is we put this little squiggly lowercase delta sign in, kind of looks like a D and an S combined together, and that is a partial charge. It's hogging the electrons. Hydrogen is sort of like kind of missing its electron. It's not gone, it's just not around it as often, and so it ends up with a partially positive charge. That difference, let's get a different color here, it's partially positive and partially negative charge that exists on either side of this bond. This is a dipole, and we can actually sort of put an arrow with a little plus on its tail to show that it has a dipole. Now, realize if this is water, this would be happening twice, right? And so the same thing would be happening, and we'd have some electrons from the other hydrogen getting pulled towards the oxygen as well. So this water molecule ends up having dipoles. Its bonds are polar covalent, and this leads to the polarity of molecules, really important concept in biology. So water is a polar molecule, and it really should have these partially signs on there. It's not a full ionic charge, it's a partial charge. All right, quick summary of some of the names of the forces that keep these molecules together. So we're gonna focus on the molecules, but we'll quickly mention the ions as well. So just when you see these terms here, in biology, I tend not to use it too much in chemistry, but in biology we sometimes use the label van der Waals forces, and this is just the attraction of one molecule to another. So if you had just had some molecules, they're going to be attracted to each other. They have protons and electrons. The other molecule has protons and electrons have charges. The positives will be attracted to the negatives will be attracted to the positives. So molecules are attracted to each other. Any molecule, any sort, will have some attraction. It is pretty weak though, so it's not that strong. It's pretty weak, but that is called van der Waals forces. Then, if you have molecules with polarity to them, remember they form these dipoles, so they will have a stronger attraction. It's not just the electrons and protons being attracted, but there's actually this polarity to them. These dipoles are like, kind of think of them like magnets. They're going to be more attracted. It's not that you can't separate two magnets from each other, but they're kind of attracted to each other. And some dipoles are stronger than others, so their force can be more strong than just van der Waals forces. So polar molecules are more attracted to each other than non-polar molecules. Hydrogen bonding is like a super dipole. So it really is a dipole force, but it's a specific type of dipole force. When you have hydrogen, notice that the name hydrogen is in the label here. So you have to have hydrogen bonded specifically to oxygen, fluorine, or neon. Not all of them, just one of those. If you have a hydrogen bond to an oxygen, or you had hydrogen bonded to fluorine, or hydrogen bonded to neon, you can get hydrogen bonding. And the reason is, think about it, those three atoms, the special thing about them is that they're like really electronegative. So they have high electronegativity, nitrogen, fluorine, and oxygen. So they really hog hydrogen's electrons, making them quite negative and hydrogen quite positive, giving you a really strong dipole. And it's so strong it gets its own name called hydrogen bonding. So they will stick together really well. Then, if you have like think of an ionic bond, it's kind of like something that's so polar it's not even called polar anymore. It actually loses the electron. It transfers the electron over. So you actually get full charges, you get ions, and you get ionic compounds. So quick overview of van der Waals forces. Another name for them, London dispersion forces. And so London forces, dispersion forces. These are, again, since the atoms have electrons and protons that make up a molecule, and another molecule has atoms that have electrons and protons, those charges will be attracted to each other. And so again, these are very weak forces, but they're always present. The larger the molecule is, the more electrons and protons it has, the more attracted it will be towards other larger molecules. So all compounds have van der Waals forces. They're all going to be attracted to each other. If it has more atoms, there's more of an opportunity for this force to exist between one molecule and another molecule. The more surface area the molecule has, is what this diagram is showing, also gives you more opportunity. So if a molecule is all clumped up together, it's going to have some London forces or van der Waals forces attracting to another molecule here. But if it is more spread out, even if it has the same number of atoms, there's more opportunity for that attraction to exist, and therefore it will actually be a stronger attraction. So all compounds have van der Waals forces, but the bigger the atom is, the more force you're going to have, and the more spread out the atom is. Sorry, I'm saying atom. The bigger the molecule is, it could be made of bigger atoms too, but basically the more electrons, the more protons you have, the stronger the van der Waals force is. The more area there is for this to be exhibited also leads to stronger van der Waals forces. Dipole forces. So remember, this is when you have polar molecules. When you have unequal sharing of electrons within a bond, you can end up with, take a look at this guy, it's got a positive pole right here, and it's got a negative pole right here. And so if it were to bump up against another molecule that has a positive and a negative, so think of these dipoles here can line up, and this negative end is going to be super attracted to this positive end, so you end up with a stronger force than what you'd have with just van der Waals forces. So dipole attractions, or polarity, is going to be stronger than van der Waals forces. It's not that there aren't van der Waals forces here. They're here. They're just super weak compared to this strong dipole attraction. Then there's hydrogen bonding. Now, if you understand what a dipole is and how dipoles can be attracted to each other, one dipole to the other, that's just what hydrogen bonding is. It's just a specific type of dipole. So again, this is an intermolecular force, between molecules force. And you have this negative and positive end to the dipole. It's going to be attracted to the opposite charge of another dipole on a different molecule. But remember, you have to have this with nitrogen, oxygen, or fluorine bonded to a hydrogen. So a hydrogen bonded to a fluorine, or an oxygen, hydrogen bonded to an oxygen, let's do it that way, or a hydrogen bonded to a nitrogen. Now realize these are not stable molecules, right? There'd have to be some more bonding going on there, but this would be one part of it. There's going to have to be more bonding on there as well. So there'd have to be something else bonded here. There'd be two things bonded here. But where that hydrogen oxygen or hydrogen nitrogen or hydrogen fluorine bond are, you're going to have a really strong dipole, and therefore you're going to get what's called hydrogen bonding. So here is, let's do this in green. Here is a super strong dipole. It's still a dipole. It's just a super strong dipole. And look here, there's another super strong dipole. And it is super strong because it is oxygen with hydrogen in both of these molecules. So when you have this super strong dipole up here and this super strong dipole down here, the force between them is called a hydrogen bond. Quick mention of some nomenclature in organic chemistry. So again, carbon's super important. There's going to be a different number of carbons, and we can say how many carbons there are with the prefixes listed on the right here. So when we want to say that there are there's a single carbon, we use the prefix meth, and there's more to it than this. These can be branches, these can be entire molecules. So this is just a quick overview of it. But for example, you may recognize the name propane or butane. And so what that's telling you is propane is a molecule that has 3 carbons. Butane is a molecule that has 4 carbons. So the number of carbons can be depicted in the name. Isomers, quick definition of them. Again, we talked about isotopes. Don't get them confused with isomers. Isotopes, you're talking atoms. Isomers, you're talking molecules. And they're made of the same atoms. Isomers are made of the same atoms. So if you looked at the actual formula of the molecule, it would be the same. So this one here has 5 carbons to it. And we've got 3, 5, 7, 9, 12 hydrogens there. And this is a particular molecule. Now, you can take the same atoms and build them differently. I think it's like Lego, right? Like you could take some pieces of Lego and you could build them a particular way, or you could build them another way. This is a molecule that is built a particular way, or you could take the same atoms and build it another way. These are different molecules now, but they're made out of the same things, the same atoms, the same type of atom, the same number of atoms, but built in a different way. That's an isomer. Because of this, we need to give them different names. So this first one is called pentane. And again, there's that prefix there, pent. That's referring to this one having 5 carbons. And it has an isomer called 2-methyl butane. And again, look at the formula. The formula is the same. That's what we mean by isomer, but it's a different way of building it. So we got to give it a different name as well. There are structural isomers. So we're going to get into talking about glucose and fructose. So there's a quite different arrangement in them. Same formula again. They are isomers. They have to have the same formula, but slightly different bonding between them. And so we can look at, if you look at glucose, you look at the structure here, and you look at fructose, you can say, okay, yeah, those are definitely different structures there. Then there are things called stereoisomers, and they are different, but not as different as you think. So, for example, glucose and galactose are geometric isomers. So if you look at these formulas here, see if you can find the difference between them before I do. There it is. If you look at this OH, so everything's the same, except for this little OH group and this hydrogen are switching spots. So that gives you glucose or galactose, depending on which way it's going. And generally in chemistry, there's probably not a whole lot of difference as to what happens with the isomers, so they tend to stick to structural isomers. But in biology, very small differences in the molecule end up having huge impacts on how that biological systems work, because shape's so important in biology when it comes to molecules. So we start talking about really specific types of isomers. So these are geometric isomers with just a little change here. They have similar chemical properties, they like burn the same, but they would actually have different physical properties. So you can have, in terms of how they act with their physical properties, and I have to look up glucose, galactose, but they will have slightly different physical properties to them. Then there's even harder to tell the difference between called optical isomers, and we'll just mention these guys. We won't focus on them very much. But if you look at a molecule, these are essentially mirror images of a molecule. So if you think of it like your left hand and your right hand, you could think of them as being optical isomers of each other. If you try to describe how they're built, they're kind of built the same way, right? You've got a thumb on one side, you got 4 fingers, but they're a mirror image of each other. So those are optical isomers. And again, chemically, very, very similar, but in biology, that shape makes all the difference. Last thing to mention is monomers and polymers. Mono meaning one, mer meaning like a thing. So one little thing would be a monomer, and poly means multiple. So if you have a bunch of little mers, little things, that would be a polymer. So what you can do is you can take monomers and you can string them together and you get a polymer. And then there's, of course, in between, you say, oh, we have 2 of them, we can call them di something or others, whatever they happen to be. So if they're saccharides, when they're by themselves, you can call them monomers. You put them into pairs, you can call them disaccharides. And then you put them into long strings, and they're called polysaccharides. And so this is one of the ways that biology happens, is that you take these small units and you start putting them together into larger, complexer patterns, and then you can get complex molecules and you get life using monomers and polymers. And remember, merge is a generic term, so we're going to see how this works with sugars. We're going to see how this works with proteins. We're going to see how it works with amino acids. They can all take individual pieces and build more complex patterns.